Okay. Um, Hello. Welcome to the first of 3 discussions on your project. What we're going to be discussing this time is how do you power your circuit? So I'm going to go off of a couple of assumptions here when we're discussing power. First of all, assumptions, and this is going to dictate really how I am designing this. You don't have to make these assumptions. You can figure out a different way to do it if you really want to. But since this is kind of an introductory class, might want to listen up to this. So some assumptions that come into this project is, first of all power is going to be supplied by the Raspberry Pi. Okay, what does that mean? It means I don't hook up any external power supplies. I'm not hooking this to a wall outlet. If there is something in this circuit that's going to be powered, it's going to derive its power from the Raspberry Pi. Because a Raspberry Pi is has an integrated board on it, it can transfer power that way through the input-output pins. We're just going to assume that's what's going on. Okay, so that's our first assumption. The second assumption is that we want to try to minimize the amount of power that's coming out of the Pi while still maximizing the amount of light that's coming out of our display. Okay, it's not that hard to come up with, just, hey, look, I made light, and it's very, very dim. Really low power consumption if you have that, but with these assumptions, this is basically what I'm going to use to build my circuit, knowing these things. Okay? So now with this behind us, going into the project, again, you can violate any of these 3 that you want. You can try to maximize your power consumption, although if you try to build it for real, you may cause your Raspberry Pi to get a little funky. This is, in general, these 3, if you're building a project on the Raspberry Pi, you want to abide by these 3. Now, it's not always possible if you're powering a motor or some high power component. Then you certainly are not able to supply all the power through the Raspberry Pi, in which case then you were using the Pi only as an informational directional source. You're trying to minimize the total power consumed by the Pi. That's something else. Why do we want to minimize the power consumption by the Pi? Well, if you're minimizing the power consumption, first of all, it means the Pi is not going to heat up as much. You're not trying to put as much power through it. Second of all, it means you're not putting as much power through each of the individual I/O pins on the Pi. That can cause them to burn out over time. It can also it can create heat. And you really don't want to heat, that's energy lost. If your Pi heats up too much, it may shut off. So if you follow through this, minimizing power consumption, maximizing light production, we can try to come up with something productive here. Okay, so let's go into next, how is it that you take a light and actually produce light from it? Okay, so a little LED, you get it, it looks like this. We played around with them a little bit in class. Here, this is the positive end, this is the negative end, or the ground pointing end. LED powering is not like normal resistors. This itself is not a resistor. It's what's referred to as a diode. Okay, and LED stands for light emitting diode. A diode looks like this. Now, if you remember from our digital circuits, this is the symbol for an inverter. Okay? So if we take the circle off the front of it, what it means is if we have a true signal coming into this, we have a true signal coming out of this. That's what a diode is. It doesn't change the value any. In fact, what a diode does is it takes whatever power is coming in, it prevents power from going the opposite direction. LEDs only operate in one direction because that's how diodes work. Diodes operate off of a transistor principle where the resistance to current flowing in this direction is very, very low, whereas the resistance to current flowing in this direction is very, very high. We can always talk about that at another date. I was supposed to talk about that in this class, but we won't get to it. It all has to do with P and N type material, P and N dope type materials. We'll probably end up talking about that at another time, so keep your ears peeled. Anyways, this is a diode, and the way that this consumes power is it consumes a very finite amount of power. The way that you control the brightness of an LED is not through voltage, but it's through current. Every LED has what's called a forward voltage. When you purchase an LED, it usually has a set forward voltage that it uses, and that it operates off of. When you go to plug in an LED over this forward voltage, what happens is, let's say we have a DC source, and then we've got, here's our LED, and here's some kind of a resistor, okay? So this is 5 volts. If we have a forward voltage of 2.2 volts here, what's going to happen is that this diode will allow current to pass through it without producing any light until it reaches 2.2 volts. Once it reaches 2.2 volts, then what will happen is this will only ever consume 2.2 volts. All of the rest of the voltage for this entire circuit is consumed by the resistor. Okay, so then this takes 2.8 volts. Right? Now I did say that the amount of light being produced by the diode is controlled by the amount of current flowing through it. It has a constant 2.2 volts. It has to have 2.2 volts just to turn on. But then you increase the brightness by increasing the amount of current going through this. Okay? How do we increase the amount of current going through this in this circuit? Well, we decrease the resistance. Remember, higher the resistance, the lower the current is going through it. Well, here, if we decrease this resistance, we'll increase the amount of current going through this. Now, there's a peak threshold to the amount of current that can go through that diode. And basically what you have is this is treated as a no resistance piece here, but you just have 2.8 volts across your resistor constantly. So if this is a 2800 ohm resistor, you have 2.8 volts going across it. What that means is you're going to have, I equals V over R equals 2.8 divided by 2800. This is going to be equal to 10 milliamps of current flowing through there. Okay? 10 milliamps of current it's actually something that you probably want. 10 milliamps of current is a very desirable range when it comes to a Raspberry Pi. Each of the pins, not sure if this is the case in the Raspberry Pi 4, but each of the pins was capable of putting out 50 milliamps of current to each individual pin for the Raspberry Pi 3. That might have been increased to 100 for the Pi 4. I'm not sure. Pi 4 I know is more powerful and yet consumes less power. So here's the number that we're going to be aiming for, though. We want to output 10 milliamps of power through each of the pins. Okay. Now in total we have, when we go to build our display, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're going to have 14 of these. So in total, we're going to end up with 0.140 amps of power being output through, amps that are being output through all of the systems. Okay, this is a good number, not a bad number. So this is kind of our target here. Now the lights are not going to be as bright as they possibly can be. If you increase the current here to 5 to 50 milliamps or even 100 milliamps, approaching that limit of what the Pi can handle, your light is going to get significantly brighter. But it's generally not good, because then we're no longer minimizing power consumption, and there's no way we're going to be able to power 14 of those off of, every one of them getting 100 milliamps of power. So not the best. Okay, so when it comes to designing for LEDs, you have to know the forward voltage. For this project, I would say assume that your LEDs have a voltage of 2.2 volts. Okay, which means you're going to want which means that when we power these, if we're going to power them off of the pins, it's not 5 volts, it's 3.3 volts. Okay, which means this is 1.1 volt. Okay, so we have 2.2 volts being consumed by the actual LED, and then a 1.1 volt across the resistor that's controlling the current. Now once again, we want to end up with I is equal to 0.01 amp. That's kind of our target value. So how much resistance do we need to have in this resistor to get about 10 milliamps of current? Well, we just use Ohm's law again. Okay, we know that this has 1.1 volt across it, and that is controlling the amount of current that is passing through that LED. So what we'll do is we'll say, okay, R is equal to V over I. We know we have 1.1 volt, and we know we have 0.01 amps, which means we're just multiplying this effectively by 100. Okay, and we end up with 110 ohms. If you can find 110 ohm resistors, this is perfect for what we're looking for. Okay? So now we know the value of the resistance that we're going to use to put in series with our LEDs. This is going to give us it's going to give us a basis for how we can design this now. For a lot of LED screens that are actually dedicated LED screens, they will only have a power supply that produces the forward voltage of the LEDs. Why? Because then you minimize the amount of power that's going through the resistor, which that's a good thing. Okay, minimizing power loss. All of your power being consumed is going through the LEDs and is coming out. And by controlling the current output of the power supply, that's how you can control the light. Okay, so we figured out the resistor for the LED. Okay, now the next step of something that we have to figure out is the button. Buttons are not easy to sit down and build into a system. Okay, if you're going to put a button into an electric system, well, let's talk about it. Here's our Pi here. Okay, here is our two basically multimeter points. Okay, we have to have 2 points because there has to be a voltage difference between the 2 points. Okay, this is voltage A and voltage B. The difference between voltage A to voltage B is ultimately what dictates whether or not there is a voltage. We're going to take B and we're going to go ahead and ground B. B is going to be ground. So, okay, great. Now, when we're measuring A is going to be measured relative to ground. So what ends up happening is, on your actual Pi, you're going to have one read port, only one, and that one read port, A, is measured relative to ground. Okay? So we don't need to hook up a B as long as whatever the button circuit that we have is grounded somehow. Okay? A is kind of like our test port 1, B being the ground is kind of like our test port 2. We're going to use that. We're going to touch our button and figure out whether or not the button is on. In a conductivity-based circuit like this, so usually the way that a button looks, we got this black here, little box. It's got 4 pins on it. What happens is these 2 pins here are connected. It's one wire. This wire then goes up into the button, and then pressing it causes a second wire to basically depress that touches both ends. Okay, this is an omnidirectional button. It doesn't matter whether you put it in this way or this way, it's still going to operate, because all it's doing is when you push the button down, it attaches a wire that connects both of these 2 terminals. Okay? So that's how a button works. Great. So how do we read a different voltage across A when we're plugging in a button? Well, it's not quite intuitive. We know that there's 2 ways of doing it. One is if button is pushed, A equals 5 plus volts, and if button not pushed, A equals 0 volts. Okay, this is method 1. Method 2 is the exact opposite. If the button is not pushed, A is 5 volts. If it is pushed, A is 0 volts. Okay, so that's the 2 different ways that you can hook up a button. I'll show you the difference between the 2. We can talk about it that way. So we know we need to have these 2 conditions. Okay, what we're going to do right away is we're going to say, I'm going to take test port A and I am going to hook it into this end of the button. Okay, so here's my button. It is directly connected to that end of the button. Okay, and then I got this end of the button. Well, if I just, that a lot of people, what they do when they first hook up a button is they'll say, okay, here's my ground port. Well, I'm just going to hook it up like this. Well, the problem is that when this is pressed, A is going to be equal to the ground port. When this is not pressed, you release that. There's never been any voltage that has been supplied into this end of the button. So this A is still going to read ground. Okay, then they say, okay, well, another common mistake when hooking up a button first is, oh, I can't get any power into this. I'm going to plug this into 5 volts, or I'm going to plug it into 3.3 volts on my Pi. So this end of the button, if I push it, it's 3.3 volts, and if I don't push it, if I let go of it, then this suddenly becomes 0. Well, that's not quite true. With a button in this configuration right here, if you push this, then yes, A is reading 5 volts, because basically what you've done is you've connected a wire here such that the 5 volt terminal and the A terminal are connected, and A is reading and it's saying, oh, it's 5 volts. When you depress the button though, and you disconnect it, that energy doesn't go anywhere. A is still going to be reading 5 volts because the energy is now trapped in this end of the button. This is where we need something called a pull-up or a pull-down resistor. Now in this case, a pull-down resistor is going to give us condition 1. A pull-up resistor is actually going to give us condition 2, where those 2 are flipped. I'll explain it now. Okay? So what we have here in our button, for the button, we have, so once again, here's our button, here's the terminals on the button, and then I'm going to go ahead and I'm going to connect this to port A on a Raspberry Pi. This could be port 5, this could be port 7. It's something that is reading whether or not a voltage is applied at this terminal, okay, to see whether or not the button is pushed. What I'm going to do here is I'm going to say, okay, I want this to be grounded. Okay, so this will go into, extend this a little bit. This will go into a ground pin. Okay, I'm putting a resistor here that goes between the button end and ground. I'm going to go ahead and I'm going to make this 2.2 kilo ohms. You want it to be kind of a high resistance. Sometimes people will even use 10 kilo ohms. Why? Because it really reduces the amount of current that's going through here. And one thing we learned in class is that your power consumption is equal to V squared over R. If we increase the R value, we are going to be decreasing that amount of power that's being consumed by that resistor. So, increasing this doesn't hurt. You mean you don't want it to be like mega ohm resistance, because then at that point it kind of takes a while for this to dissipate. But 2.2 to 10 kilo ohms, that's a good range for a resistor there. Okay, now this here is called a pull-down resistor. No, sorry. Yes, no, that's right. This is a pull-down resistor. What this does is when this button, oh, and then we take this end and we hook it into 3.3 volts. Okay, what happens is when this is depressed, we're connecting this here, and there is a direct wire that goes from 3.3 volts to A. So A reads 3.3 volts. That's an on signal to a Raspberry Pi. Okay, anything I believe it's above a 2 volts is considered on for a Raspberry Pi. I think that's it. So 3.3 volts read directly into A. When this is not depressed, what happens is, as soon as we release this button, this terminal right here is still 3.3 volts. So is this one. Okay? That momentary release, we don't see a voltage change, a dramatic voltage change. There is some parasitic effects in every system. Here, there is a little bit of capacitance that prevents that voltage from rapidly changing. And what happens here is instead, now we have a location for this to go. This then, all of that voltage goes through this resistor to ground. Okay? And now, in order for A to have any kind of voltage, there would have to be a consistent current through that resistance. Well, there's not. There's nothing to power. There's no power on this side. So what you have is there's no current going through this resistor as soon as all the energy dissipates. So this is forced to ground. It is pulled down. Okay? So in this situation, when you push the button, 3.3 volts is directly shorted to A. When you release the button, this is grounded through a resistor. That's why it's called a pull-down resistor, and that's how you end up with this situation. We can do it the other way. Okay? I'm going to switch. I'm going to put 3.3 volts here, and I'm going to put ground here. Okay? And this is, again, going to be a 2.2 kilo ohm resistor, or a 10 kilo ohm resistor, or a 1 kilo ohm resistor. Something in that range. You probably want a kilo ohm something, because you really want it to reduce the amount of power that's being consumed. And what's going to happen here is when this button is not being pushed, there's no current flowing through here because A doesn't consume any power. So A is forced to 3.3 volts. Okay? This is now not a pull-down resistor, this is a pull-up resistor. When we push the button, A is directly connected to ground. There is now power flowing around A from the 3.3 volt through the resistor that I just raised with my finger, through the button, and into ground. Okay, we now have power that is flowing. It's a very small amount of power because we have a very high resistance in our resistor. But A is directly connected to ground here. This is called a pull-up resistor because when it's being pushed, the opposite of this case happens. Okay, when this is being pushed, if button pushed, A is equal to 0 volts because it is directly connected to ground. If button not pushed, then A is equal to 5 volts. Okay, so this is the difference between a pull up and a pull down resistor. And being able to put a pull up or a pull down resistor is really important in this type of a system. Okay, now I'm going to go ahead and specify. There is the ability to, on the pins, there are actually built-in pull-up and pull-down resistors. If you feel comfortable and you are knowledgeable in how to code those in, you can do that. I'm not going to be pursuing that route in this class. I'll probably teach it to you in 350, whenever you take 350. For the majority of this, I'm actually going to physically put in a 2.2 kilo ohm resistor for the button. Okay, we only have one button, so it's not really that challenging. Okay, so just to recap, I'm giving you all this information right now because we're building into the idea of we want to be able to actually physically build a wiring diagram now. Okay, so the components we're going to need, we need 14 LEDs. Why do we need 14 LEDs? Because that's our 2 numerical digit displays. Okay, so 14 LEDs. Now, because our power supply does not put out 2.2 volts, and I'm assuming that each of these LEDs put out 2.2 volts, or have a forward voltage of 2.2 volts, it means that for each of these, we're going to need 14 resistors. Okay? We need one button. For this one, we need one resistor. Our 14 resistors, we determined to have a value of 110 ohms. Okay? That's to create that 10 milliamp current that's going through the diode. Okay, and here we have one resistor that gets connected to the button, and that is going to be, we're going to go ahead and say 2.2 kilo ohms. That's what I'm used to. Okay, so we have 15 resistors total, 14 LEDs, one button. It's going to require 15 different ports on a Raspberry Pi. That's kind of a lot. Just grabbing my Pi real quick while you stare at my board. I'm actually not going to come back in the camera view. I'm done. No, I'm kidding. If we look at the T-cobbler on the Raspberry Pi, see, my lighting in here is terrible. I don't know if you can actually see. Yeah, no, I think I would have to. I'm not that good with cameras. But we don't have a whole lot of ports on here. While you do have 40 pins total, I do believe we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13. Yeah, we definitely have 14. I believe there's something like 22 individual I/O pins, a number of grounds, a number of power ports, a PWM pin, and a data and a clocking pin. Anyways, we do have a total of 15 ports we can do on this. But let's say we were going to be trying to use an Arduino or something to power this, and we didn't exactly have that nice, I have 15 different pins to power these LEDs. What if we wanted to use the very minimum number of pins possible. Okay. This runs into how do we take information from the Pi and send information to the LEDs. Okay? How do we do that? And we're going to do it in the form of power. How do we send this? Well, there's a number of ways to send this. Okay? If we have a parallel registry, we can have 14 individual pins submitting information simultaneously. And that's called sending information in parallel. Okay, that means you have 15 pins that are being turned on and off according to what the LEDs are needing and reading information according to what the button is reading. 15 pins simultaneously. Serially, what we can do is we can have this be anywhere between 1 and 14 pins. Okay, and the idea here is that different times correspond to different pins. Like it may be transmitting a signal to the pin for 1 millisecond, it goes to LED 1. And the next millisecond is LED 2. The next millisecond is LED 3. Okay, so every one cycle of talking to every single LED and talking to the button corresponds to 15 digits, so 15 milliseconds. So every 15 milliseconds you'd have different signals, and it would take that byte data on or off for each of these, and it would be submitting that 15-digit word across one pin to really control everything. That is possible. Serially, minimum number of wires that would be needed. For our configuration to try to do something serially is actually really challenging because you have to have a decoder, you have to have an encoder so that the system knows, okay, I'm sending out these numbers of digits, and then the LED board knows, okay, I'm receiving these number of digits, I then convert it into this. The way that a lot of TV screens work is that they have a number of parallel registries that operate serially. So you don't have, if you have a 1280 by 1800 display, you don't have 1280 by 1800 different pins on your control board controlling every single LED, or even more than that, 3 times that number or 4 times that number, because you have white, green, red, and blue lights for your LED displays. So that's a lot of wires that would be needed. They have to do serially. They have to, because there's too many wires there. We're going to be doing parallel because since we have such a simple display, we can do it this way. We don't have to deal with encoders, we don't have to deal with decoders, we don't have to deal with any of that. It's kind of a dummy system. We can always make this more advanced later on in life when you have absolutely nothing to do and you want to really inefficiently build something that already exists. Awesome. Okay, we're going to be doing it in parallel, which means we're going to have 15 different pins being used simultaneously. There is a way that we could do it with 5 pins, and then what you have is you have a number of AND gates that control each individual LED. So every LED would be connected to an AND gate, and if all the conditions are met for that LED to turn on, that AND gate would turn on too. Okay, that is completely possible to do with 5 pins. We could build a digital circuit that does that. I don't want to do that as a part of this project. I made everybody do it last year. I don't want to do it this year. Okay. Here, every one of these AND inputs would require those 4 pins, and then whether it's, here you would say 0, 0, 0, 0 turns on pin number 1, and 0, 0, or turns on pins number 1, 2, 4, 7, etc., etc. Okay. I don't want to design it this way. I don't want to force you to design it this way. We're just going to go with a very simple way of let's just build it in parallel. Okay? So, now we know all the components we need. We know how we're going to transfer power and transmit information from the Pi to the LEDs. Let's go ahead and draw what would the breadboard look like. Okay, so here's my breadboard. I got my center gap in the middle where there's no connections. I got my 2 pins on the sides where there's a metal bar that runs vertically on these 2 pins, connects all of these 2 holes together, but all of these pins here are connected with horizontal wires. So that's what we're going to do. Now, more than likely what I'm going to have is I'm going to say, okay, let's say I'm actually going to build the LED display on something that is 3D printed. Okay, let's say I'm going to have 1, 2, 3, 4, 5, 6, 7. Okay, let's say I have a system that looks like that, and those are my numbers. How do I control all 14 of those LEDs? Well, every one of those 14 LEDs has to be attached to a resistor, 110 ohm resistor. So over here, I'm going to have a pin input. So if I have a T-cobbler, okay, what I'll have is I'll say let's say right here we have a resistor that's going to go from this pin to this row, okay, and then from this row that is going to go to the positive edge of the LED, and then from the edge of the LED it's going to go back to our ground pin, okay, or what would probably be easier than that even is rather than having a ground pin, you actually use these 2 vertical running pieces right here where all of these are connected. If we take one of these and we jump it to ground, okay, and then we take the other end of this and we jump that to this LED, we can use that ground for every single one of our LEDs. Okay, and you can already see this is starting to get a little crazy. This is getting very messy very quickly. Okay, so if we're going to try to draw it, this is realistically the way that we're going to build it. We now have to say, okay, I'm going to take a resistor off this pin. It's going to go into this row here. This row, I'm going to go over here and pop into that one. We got a resistor here. It's going to come off that one. It's going to go into this row. We're then going to read off this row, go into that LED. If we're going to try to draw it this way, which is realistically how it's going to get built, it gets very messy very quickly. 14 wires, which now becomes 28 wires touching these because you have an input and an output wire for each one of them. Wow. Okay, now let's say, all right, we're going to do this smarter. Okay, I didn't teach you how to do soldering this semester because we didn't have time. Rather than having 28 wires coming out of this board, with all 28 of them going in there, you know what I'm going to do? I'm going to connect the ground wire from this wire all together. All the grounds are going to be connected. Because they are all going to ground, I might as well connect them to some common ground pin here. You can do that by connecting them with a ground wire. This is what a lot of real electrical systems do, is they'll have all the grounds connected together inside of a system so that when it comes down to it, the number of wires coming out, you only end up with 15. One ground wire, which this could either go into the ground pin here and then gets routed up there, or it can go directly into the ground. And then you have your 14 different parallel connections that determine the light for each individual light. Okay? So that would minimize the number of wires that's going into this. That's probably something that I would recommend. Now, how do we, this is still pretty ugly to draw though. 15 wires going into that? That's a lot. So what we're going to do, instead of drawing it realistically, which this is the absolute cleanest we can possibly draw at this point, instead of trying to draw it realistically, what we're going to do is we're going to draw a representative diagram. This is called the wiring diagram, okay? A wiring diagram is a way of well, it's what we've been dealing with in class so far. Every time we draw something that looks like this, I mean, that's a wiring diagram. That's what it is. Simply put, that's how you draw a wiring diagram. Now, one thing that we can do to try to clean this up, we have multiple wires now. There is a more effective way of drawing this. Now, this allows us to draw closed loops, but another way of drawing this system that's especially used with larger systems is what you'll have is you'll have a power input, so say that's a plus, you'll have your component, and then you'll have ground. This is the exact same circuit as this. It does the exact same thing. The only difference is this takes up a lot less space. And if we're going to be having multiple components, we're probably going to want to draw something like this. Okay, now I'm actually going to label this as a pin number. Let's say this is pin number, let's see what's a good pin number, 21. Okay, I have 21, goes into a resistor, that goes into an LED, that goes into ground. Okay, that's all I need to draw for that entire wiring diagram. Now, realistically, over here, the situation where it's actually physically configured, I showed you you'd have to run this wire in, and then you have to connect all the grounds in there and have the ground wire come back out. Yes, that is the case, but the way that we're going to represent it is like this. Much, much simpler. Okay? And I'm actually going to show on my wiring diagram that all of the grounds are connected together. Okay, so we have led to this point, this entire discussion. What does it look like to actually physically build this system? What is the wiring diagram for this? And what is it that I'm requiring for your project? I'm requiring you to draw a wiring diagram that looks something like this. Okay? So here we have, we're going to represent the Raspberry Pi with a box. Okay? Why? If you remember from our discussions on the digital components, we represent those components by boxes. And the inputs and the outputs are just wires that come out of that. It's pretty typical for a digital or an analog component like this. Okay? So we're going to take this and we're going to say, I'm actually going to list out 21. Okay, 21 goes into a resistor. I'm going to call this resistor A. And then we're going to have another port. Let's say this one is 5. Okay, 5 goes into a resistor. We're going to call this one A also. Why? Because they're the same resistance values. And then this is going to go into an LED, which the ends of these then get connected. Okay? And I'm going to keep drawing this. Ends of them get connected. Keep drawing this. Ends of these get connected. Keep drawing this. Ends of these get connected. Okay? And I'm going to draw this 14 times, and I'm going to have one ground. Okay? So 14 of these. And then lastly, I have my button. Now this is my, to draw the diagram for the button, I actually have to have power. So I'm going to represent this by the 3.3 volt output of the Pi. I'm going to have this be a pull-down resistor because I prefer the pull-down method where when it's being pushed, it reads an on signal. You can code it the other way. That's completely fine. If you want to try it that way, more power to you. But what I'm going to have this is this goes into a button, which a button is represented by a switch. Okay? which then this connects to pin number, let's see, what's a good number for this one? We'll say 17. So this is plus 3.3 volts, goes into a button, which goes into 17, which then gets connected to a resistor that gets connected to ground, okay? And we'll label this resistor B. So all of these are listed A, this one is listed B, and then we say down here, A equals 110 ohms, B equals 2.2 kilo ohms, okay? This is a wiring diagram. And this is a sufficient wiring diagram to show how we're going to hook this up, okay? You have to provide me with one of these. Now, I didn't draw all 14 of these inputs. You can draw that yourself. Quite frankly, I'm spoon-feeding the answers to you at this point, and you're getting credit just for watching the lectures. But you have to give me this as part of your final report. It's okay if you want to draw this on engineering paper and scan it in. It's okay if you want to try to draw this in AutoCAD. It's okay if you want to try to draw this in SolidWorks. That's also completely fine with me. Okay? But you should end up with something that looks like this, and it should be fairly nice and easy to read. Okay? At this point, with me having just given you the answers, there's no reason why you wouldn't give me something nice that looks like this. Alright, we're going to be covering coding and any final discussion on the project in the next 2 lectures next week. Again, this is your only assignment due for the remainder of class. Make sure to hand in your old homework assignments, please. I have stopped giving you homework assignments as a way of trying to help you have the time to turn these in. 2 weeks from now is the end of finals week. That's it. That's all you have. 2 weeks. So if you don't get it done in 2 weeks, you're not done. You get whatever grade you get. I have been fair in my opinion, and I have tried to be kind. But you have to put in the work. This is your education. You are still paying to be a part of this class. So please take this seriously. Let me know if you have any questions. I am always willing to meet with you one-on-one, have a Zoom meeting, cover any of this if you need it. Just send me an email. We'll schedule a time. Okay? Otherwise, I'll talk with you about programming on the Raspberry Pi on Tuesday, and we'll finish out this. Okay?